So we do this solution iteratively. First guessing a model, then doing a forward solution, calculating the spectra, the parts of the spectrum that we're interested in, comparing those with the observed spectra, adjusting our model, and iterate till we converge, right? And we'll show you a little bit more formal how that works. So if there's anything I would like you to take away, then these are the two main points. Just again to reiterate so that we know what we're talking about, the equation of radiative transfer. We have emission and absorption. Oops, no, not that. Oh, I guess I must have pressed the wrong button. No, my screen is blank too. So.
Oh, it happened to someone that couldn't project and had to go through this. Maybe it was Eva. Yeah. Try again.
Okay. I may have hit the wrong button. Okay, so we have emission, we have absorption, we have the transport equation along array, and we can define the optical depth tau. In this way, remember the minus sign, because optical depth goes into the atmosphere, well, Z goes up. And so we have the equation of radiative transfer with the source function, the ratio of the emission and the absorption coefficient. We can rewrite this equation as an integral equation. In this case, for the emergent intensity at optical depth unit R0, the top of the atmosphere, it's just the integral of the source function times e to the minus tau d tau. Remember though that again this is not in general a closed equation because this source function here depends on the intensity itself, especially in the case of non-LTE and in the case of scattering. Right? So this is again a deceptively simple expression, but it is, we use it formally to express how the intensity depends on the source function. Ivan showed you the polarization. Light is a plane parallel well, we usually view light as a combination of plane parallel electromagnetic waves, where the electric field and the magnetic field oscillate in a plane perpendicular to the direction of propagation. If you have a phase difference or an amplitude difference between the two directions of the electric field, the oscillations of the electromagnetic field in that plane perpendicular to the direction of propagation, you can have polarization, which is measurable with the devices that we built, as Ivan showed you yesterday. Right? In this case, when we have the amplitude and in the x and the y direction of the oscillations of the magnetic or electric field at the same amplitude, and we have a zero phase difference between them, we have linear polarization. You can imagine they oscillate like that, right? And so you have polarization that is like that. If they are the same amplitude, and if there's a phase difference between those two perpendicular directions of 90 degrees, you have a circular polarization. Your vector, your resulting vector traces a circle while the light propagates. And the Stokes definitions, Q and U, are just the net linear polarization in one direction minus that in the other, or the net polarization in one direction minus the perpendicular one, and U is that at 45 degrees, and Stokes V is the net circular polarization. Instead of a scalar equation of radiative transfer, we now have an equation of transfer for the four Stokes parameters. So here, I and J are the 4 vector, and K, the propagation matrix, is now a 4 by 4 matrix. And you can see that this is even when the regular transfer equation is sometimes hard to solve, most of the time because S depends on I, intensity. This is even more difficult to solve because you have to solve this whole set of coupled equations that are really, most of the time when there is when there's magnetic field, all of these components are non-zero. Looking closely at it, you see that there are actually only 7 independent. There's not 16 independent variables. So now let's look at an atmosphere that has physical parameters A1 through AN that depend on the position in the atmosphere as indicated by the value of tau, the optical depth. And we know that the absorption coefficient alpha and the emission coefficient J depend on these parameters, right? The alpha, we know that alpha, for instance, through Zeeman splitting, the line profile splits, alpha will broaden when the temperature is higher, or alpha will be slightly shifted in wavelength when the partial that we are considering moves. So all of these parameters appear both in the absorption and the emission coefficient. And therefore the equation of radiative transfer depends implicitly on those parameters in the atmosphere, right? And again, we can express the equation of radiative transfer in the form of the formal solution as well. Now, let's investigate what the sensitivity of the emergent intensity is to those parameters by just investigate what happens to the intensity when we perturb the physical quantity A and write down the partial derivative of I with respect to this quantity. So we just want to see how does the intensity change, or how do the Stokes parameters change when we change one of these parameters, the temperature or the magnetic field, etc. And we do this, again, by taking, writing down the equation for the partial derivative of I to one of these AJ. Let's say it's temperature. Right? So I take the equation of radiative transfer. I is J minus alpha I, right? And without using the source function at this point. Shouldn't wave my arms too much, I guess. And when we rearrange terms, you can look at this later. It's very simple algebra. You can write down the equation for this partial derivative of I to AJ, and you see that it has a very similar structure to the original equation of radiative transfer, where this is kind of an effective source function for this parameter, right? So now if we perturb I by perturbing all of the quantities, we can write this as a sum of the integral. This is basically the formal source function with this effective source function. Right? We can just rewrite the equation exactly in the same way as we did for the original equation of radiative transfer. But now we have this quantity here, and we can call this the response function, because this basically tells us if we change the atmosphere at some point, at some location in the atmosphere, say change the temperature or change the magnetic field, this is how the intensity reacts. So this is the response function of the atmosphere to changes in the variables that make up the properties of the atmosphere. Yeah, is it clear? This is an essential point, so I want to make clear that everyone understands this. You can look at the derivation. It's really simple to write down these terms and do that. So I encourage you to do that later. when you have some time. But the whole conclusion that I draw here depends on really the shape of the equation that really looks like the equation of radiative transfer itself, the scalar one. And in this case, and that allows us to write the equation really as the formal solution in a very similar way. So no questions about this? Are you all stricken or are you all understanding this? Okay, I'll assume the latter then. Speak up if you don't. So here is an example of a response function, in this case of the calcium 28542 line to perturbations in temperature. It's a kind of a funny shape. So overplotted is the line profile itself to show you where we are in the line. But this is a function, so this response function is now a function of wavelength through the line and height in the atmosphere. And what this tells you is that if I perturb the atmosphere, the temperature at this height in the atmosphere, say at 100 kilometers, right? Then at the intensity at this wavelength will change by the amount indicated in the color body on the right. Now, inversely, we can also use this and say, well, if I have a model atmosphere, I have calculated the spectrum from this model atmosphere. I have compared my theoretical or my synthetic spectrum with the observed spectrum. And there's a difference in I at a given wavelength, say at this wavelength. Then I know that I have to change, to get a better match, I have to change the temperature at this height to make the intensities match better, right? So the response function really is a map that tells me how I have to change the atmosphere to change the emergent intensity, right? This is all black here. That means that I can change the temperature to whatever I like, but the intensity will really not change because the line is really not sensitive to that height at that wavelength. Right? You also see that most of the sensitivity in the line core, in this case, comes from a higher layer in the chromosphere. And that's why this is called the chromospheric line, because it is sensitive to properties of the chromosphere. Yes?
Going back to the formal solution of the
Yes.
response function, do we have to change all the parameters, or can we just change temperatures? So what about the...
Well, so these response functions. Yeah. If we change the atmosphere, do we change it one parameter at a time, or do we change all the parameters at the same time? It's the latter. So we change we adjust all the parameters at the same time, because the response functions exactly tell us how this combination works.
So how can you have a response function just for the temperature?
I just calculated that numerically in this case. I took an atmosphere, and the only thing I changed was the temperature, and that gave me this function. Yes.
So it was not.
This is just an illustration to make the point clear that this tells me if I need to change temperature, this is where I need to change temperature. In general, you are right that this is a complicated procedure, and the solution is also not always unique. You can see that there are degeneracies, right? The width of a line, for instance, depends on the Zeeman splitting, on the temperature, because of thermal broadening, maybe also some macroscopic broadening or instrumental broadening. So all of these things are sometimes degenerate. You cannot distinguish between one of the two. In general, the procedure works very well, but there's sometimes there are problems.
Because of the way the solution is, you cannot separate just the temperature, just the velocity, just the...
Exactly,
you have
yes.
to find the combination
Yes.
all at once.
Yes. Also, it would take much too long if you were just going one parameter by one parameter, because you cannot find the solution at the same time, right? If you were just to change temperature, adjust, and then you go off, and then you have to adjust temperature again. That wouldn't work very well. One more example. This is now the response function of the same line, calcium, but now the response function of Stokes V to changes in the magnetic field. Here is Stokes V of the line. Again, function of wavelength and a function of height in the atmosphere. And now you see there's an interesting degeneracy because I see positive and negative values here. So if I say I have a positive difference between my synthetic Stokes V and my observed Stokes V, right? What do? Do I decrease the magnetic field here, or do I increase it here? Right? So there's a degeneracy there. That is not clear how you resolve that. Now, fortunately, you don't have to only fit Stokes V. You fit Stokes V, QU, IQU, and V at the same time. So that sometimes helps to disentangle these ambiguities.
Or using other lines.
It helps, of course, if you add other lines, and then that degeneracy goes away. But not many lines are sensitive at this height. That's the other thing, of course. Yeah? So now to judge whether we are successful, so we have to compare, say we want to use a couple of spectral lines, right? And we want to make an inversion of those spectral lines and infer as best as we can the physical properties of the atmosphere that cause these profiles. Now we have to make a decision. How well are we doing? And one way, of course, to judge how accurate or how close we are in matching our observed profiles is the chi-squared, which is just the square of the differences between the observed and the synthetic profiles, right? Sum over all the Stokes modes, all the Stokes parameters. Now, of course, our synthetic profile depends on the properties of the atmosphere in our model, right? That's how we calculate our synthetic spectrum. So we can take the derivative of this chi-squared, and doing some simple math, again, you can go through this later, you can see that this will give you a delta I, and of course we saw a few slides back that the delta I gives you the response function, right? So now we know that the derivative of this chi-squared depends in a very particular way on the response functions. And so basically the response functions tell us to go how to go through the multi-parameter space of the chi-squared to go to the right solution. You can imagine that there are procedures where you try to minimize chi-squared, so you try to minimize the derivative of chi-squared to all the atmospheric parameters. And you can see that involves a derivative of the chi-squared. And the chi-squared is basically the derivative that points you in the right direction of where to move your solution to get to the best solution that you can find. It's more of the derivative of the surface in multi-parameter space that tells you where to go to the lowest point. Right? You try to find a minimum in this chi-squared, an absolute minimum, which means that that's the best solution I can find to get a match between my observed and my synthetic profiles. And you have to find a way to get the roadmap. It's the Google Maps. So the response function is basically your Google Maps that tells you where to go in this solution space, which is a complicated space. I mean, you're dealing with variations on many heights in the atmosphere of many parameters. So it's a 50 or 100 parameters or so dimensional space that you're trying to find the minimum in. Yeah. Sorry? Oh, the number of what is it? The number of freedom? Degrees of freedom. Yeah. I don't know what is it?
No, NF should be number of variables, total number of variables,
Yeah.
and then you number of the parameters in the model, so then the difference is number of degrees of freedom.
Yeah. It's just the scaling. It's not just to get the absolute value in something comparable. when you compare different solutions with different number of wavelengths and different number of nodes. So now, using all of this, we have a framework for a simple framework for a inversion algorithm. And you can imagine that to do this in practice, it takes quite some effort. So we create an initial model. We use a standard solid model or whatever you want to use, something that's reasonable, but it's not necessarily, it doesn't have to be right. There's no right guess here. From this model, we calculate the synthetic spectrum and the response functions. The response functions, again, tell us where to go and to change our current model, right? So we calculate the merit function and its gradients with delta chi-squared, which then is a combination of these response functions. If the merit function is small enough, so if we iterate and it doesn't change, and we assume we're in a minimum, then the current physical parameters are the ones you saw. And we have a good match between the synthetic spectrum and the observed spectrum. And we deduce that the physical parameters that we found are more or less what the atmosphere has. There's no guarantee of that, by the way. Otherwise, we use the gradient of the merit function to point you in the right direction in the multi-dimensional space of physical parameters, and that allows you to update the atmospheric model, and then you iterate and you go back to step 2 till you finally find agreement in step 4. So that's inversions in a more formal way, in a nutshell. Again, I would encourage you to go through the equations to get a feeling for them. They're not very complicated, but any questions? Yeah.
How important is the initial guess?
So the initial guess is somewhat important. If you're really far off, the whole convergence process is a mess. So you take something sensible. You could, for instance, even use some of the techniques that we discussed yesterday, like a weak field approximation, to get an initial guess for your magnetic field. You could look at the continuum intensity at some wavelength to decide whether you are in an atmosphere that is hot or something that's cool. And then you may take a val C, or you take a val F for like a bright point or things like that. So you can make sensible decisions that help you. Now, one thing that is good to do is that once you have found the solution, is to take a different initial atmosphere and see if you arrive at the same solution. This will tell you that if there are any ambiguities. It might be that you arrive at a solution that is different. This means that, well, I have a problem because the initial model shouldn't really matter, right?
Actually, this is one way to estimate an error bar.
Yeah, yes.
You do many versions for the same profile with different initializations, and depending on where you end up, you look at the RMS of the different final solution, and you put an error bar in your inverted model. That's one way of doing it.
Can you repeat what Valentin said?
It's not that important.
No, it is. He said that it's a way to estimate the uncertainty in your solution. If you do many solutions by varying your initial solution, your initial atmosphere, and you always end up at the same, you can be pretty sure that you have a very sensible solution. If you always end up something that is very different, then you may question your methods, because then you probably don't have a really good set of observables from which to derive what you want to do, right? And then you have to make better choices in your line list, for instance. So again, varying the initial atmosphere is a way of judging what are your uncertainties in some way. Yes, you could. Yeah, sorry, yes. So the question was if you can do the same thing of with the number of nodes. Now I haven't explained the concept of nodes, and I even will talk more about this. No, basically in general you will not vary the atmosphere at every position that you have. Typically there's 50 to 100 positions through the atmosphere that sample reasonably the atmosphere. But you pick a number of locations that are representative that have a reasonable spacing, so that you limit the number of places where you vary your variables, and that your equations are not humongous but manageable. So Ivan will talk more about that. But yes, you can do the same thing and say, if I use 3 or 4 nodes in temperature, for instance, do I get a very different solution? If I do, then I have to wonder if I'm doing the right thing.